Okay, so we've now looked at a number of examples of systems of equations. We've seen that as far as the solutions go, there's sort of three scenarios that we run into. Sometimes there's one unique solution where we have exact values for every variable. Sometimes there's no solution at all, and occasionally we get an infinite number of solutions. We end up with free variables, right? Some of the variables can be assigned to parameters that take on any value, and then we can generate an infinite number of solutions. Now, a homogeneous system is one where all the constants on the right-hand side are zero, and so because the constants on the right-hand side are zero, it's impossible to run into an inconsistent system, right? One where there is no solution. Right? So why is that the case? Well, think about this guy in matrix form. We discussed in class that we can, if we let x equal to a vector containing the variables x1 down to xn, right? Then we can write down this matrix A consisting of all the coefficients, and the matrix form of this equation is simply A times x equals 0. And so what is one solution that works? Well, we know one solution that works. One solution we can take is simply x equals 0, right? So the zero solution, where all the variables are zero, is always an option for a homogeneous system, right? And so with a homogeneous system, the question is not whether or not a solution exists. The question of interest is whether that solution is unique, right? And to some extent, we don't really want a unique solution here. With non-homogeneous systems where we have numbers on the other side, often we want that unique solution. We want to know there's one right answer. But here, a unique answer is that everything is zero. That's kind of boring. If we get a non-zero solution, we'll see that what ends up happening is, if we have a non-zero solution, that means that we can solve for some of our variables in terms of the others, and that gives us some relationships among those variables that might be useful for some sort of problem that we're studying. Okay, so here's an example of a homogeneous system, right? We see that we've got zeros over here on the right, and actually we can say right away that this system is going to have an infinite number of solutions. We know that that there's not going to be a unique solution simply because we have more variables than equations, right? As we reduce this thing down, right, there's no way, think about it this way. A unique solution corresponds to a leading one in each one of the variable columns, right? We'd have to have a leading one in the x column, in the y column, z column, w column. We've seen that that's how it works with a unique solution. Every column gets a leading one. Well, there are more columns than rows, and every leading one lands in a row, so we can't possibly have a leading one in every column. Okay. So here's one where we expect something interesting in the solution. Let's see what it looks like. So we write down our augmented matrix. I'm going to put this column of zeros on the right. You don't really have to bother with the column of zeros, right? Because this column of zeros is going to remain a column of zeros all the way through. So if you just want to work with the matrix of coefficients and forget about the zeros, go right ahead. It's not really going to affect things. But let's put it there just to remind ourselves that we are really solving a system here. And let's proceed. So we've got our first leading one, right? We've got our one up here where we want it in the upper left-hand corner. So let's use it to get rid of that 2 below. So we got to do row 2 minus 2 row 1. That's going to be my new row 2. 1, 3, minus 1, 4, 0. 0. Minus 1 minus 3 gives me minus 7. 5 minus minus 2, that's 5 plus 2, gives me 7. 6 minus 8, that gives me minus 2, and I get a 0, okay, and then 0, 4, minus 2, you know what, actually, let's save ourselves a little bit of work in the next step. Notice that everything's even in that third row, so while I'm at it, I'm going to do this. I'm going to do 1/2 row 3 and make that my new row 3. Why not? 2 minus 1, 1, 0. There we go. Okay, what's the next step? The next step is to get a leading 1 in the second column. How are we going to do it? We got some choices here. Here we've got, you know, we've got a few options to consider. Okay, how do we want to do it? We could, here's one option. I could divide the third row by 2 and move it up into the second row. That gives me a couple of halves to deal with, but as fractions go, a half is pretty innocent. I could divide the second row by -7, but then I'm going to have a 2 over 7 to deal with in the fourth column. I could probably handle that. Another option might be I could take 4 times this third row here and I could add it to the second row, because 4 times 2 gives me 8. 8 added to 7 gives me 1. That seems promising. How do we want to do it? You guys are probably in the no fractions camp, so let's do it. Let's do it that way. So let's do row 2 plus 4 row 3 and make that my new row 2. Doing this, by the way, this actually generally adds steps. It makes things take a little bit longer, but we get out of fractions. Okay, so, not 0, 1, right? So -7 plus 8 gives me 1. 7 minus 4 gives me a 3. -2 plus 4 gives me 2. 0's over there. 0, 2, -1, 1. Okay. Alright. Now I got my leading 1. I can use it to get rid of that 2 below it. So I'm going to do row 3 minus 2 row 2. Make that my new row 3. 1, 3, -1, 4, 0, 0, 1, 3, 2, 0, 0, 0. -1 subtract 6 -7. 1 minus 4 -3, 0. And, well, we knew we couldn't avoid fractions forever. So let's see, what do we got to do now? We got to do -1 over 7 row 3. Make that my new row 3. 1, 3, -1, 4, 0, 0, 1, 3, 2, 0, 0, 0, 1, 3 over 7, and 0. I'm in row echelon form now, okay? But we can see that we're going to end up with a parameter here. W is going to be a parameter because there's no leading 1 in the W's column. Whenever you got parameters, it's usually desirable to continue on all the way to reduced row echelon form if you've got the patience. So how do we get to reduced row echelon form? Well, remember now we do the backwards steps. We go from the bottom right back up to the top left. I got to use this last leading 1 to make zeros above it. So I've got to do row 1 plus row 3. That's going to be my new row 1. Row 2 minus 2 row 3. That's going to be my new row 2. So 0, 0, 1. 3 over 7, 0, 0, 1, 0, 2 subtract, so I got to do this, I got to do 2 minus 2 times 3 over 7. So that's 2 minus 6 over 7, that's 8 over 7, right? 2 is 14 over 7. 8 over 7, 0. Okay, and now I add row 3 to row 1. 1, 3, 0. I'm adding 4 over 7 to 4. 4 is 28 over 7. 28 plus 3 gives me 31 over 7, 0. Okay. Again, remember that one of the things that's making this work here, these two zeros here, mean I don't have to worry about these columns when I do these backward steps here using the third row to modify row 1 and row 2. I don't destroy the work that I've already done. Alright, what's the last step? The last step is use this 1 to get rid of the 3. So there's one more step. One more step is going to be row 1 minus 3 row 2. Make that my new row 1. And I'm short on space, so let me just write down what that first row is going to look like. 1, 0, 0. And then I got to do another one of these guys. 31 over 7 subtract 3 times 8 over 7. 31 minus 24. Oh, interesting. That's 7 over 7. I just get I get a 1. Okay. Did I do that right? I feel like that's a little too easy. I think my arithmetic is okay. 31 minus 24. Yep. Okay. All right. So that would be, that would be my new row 1 eventually. Okay. So what all does this tell me in the end? What kind of relationship do I get among my variables? Let me get rid of these fractions. We don't need those so much. What's my solution? My solution is, well, I've got x plus w equals 0, so x equals minus w. Y plus 8 over 7 times w equals 0, so y is minus 8 over 7 w. Z plus 3 over 7 w equals 0, so z is minus 3 over 7 w. And, well, w equals w. W is free. Free to be whatever its heart tells it to be. There we go. Okay, so that's our solution in this case. All right, now let's think of some things we can do, some situations that lead to homogeneous systems of equations. There's a few that we've run into. One is this problem of linear independence, right? So we saw that this test for independence is, well, one way to test if a collection of vectors is independent is I set up a linear combination like this, set it equal to the 0 vector, and if my vectors are independent, then the only linear combination that's going to work here is the trivial one where I set all of my x's equal to 0, right? And we know that this gives us independence because if one of the x's is not 0, then I can solve for that vector in terms of the other vectors, and then I would know that my vectors are dependent, right? So this leads to a system of equations, right? Because if I have my vectors in there, if v1 looks like a11, a21 down to an1, right? And so that's v1, this guy here. And if v2 looks like a12, a22 down to an2. Oops, I'm missing my my x2. And so on down to xk. Right, here's v2. And if vk is a 1k, a 2k down to a nk, there's vn, and that's equal to the 0 vector. Well, you can see that homogeneous system staring you in the face, right? a11 times x1 plus a12 times x2 down to a1k times xk equals 0, a21 times x1, and so on, right? So we've got that homogeneous system sitting there. So determining independence, it basically amounts to solving a homogeneous system. Let's give it a try, okay? So we want to determine if these vectors are independent. Now notice that if we wanted to kind of set up the corresponding augmented matrix, right? How do we solve? We solve by reducing an augmented matrix, and what is that augmented matrix? It's going to be, v1 in the first column, v2 in the second column, down to vk in that last column, and if you want, you can add the zeros in. The zeros are not really important. So what we do is we let A equal -1, -2, -1, 0, 3, -2, 3, 0, -7. Okay, so we create a matrix whose columns are these vectors, and now we reduce. We figure out what the reducer row echelon form is. And if we end up with a leading 1 in every column, right, if we end up with a leading 1 in each one of the columns, that gives us the unique solution. It tells us that x1 is 0, x2 is 0, and so on. If there's going to be a column with no leading 1, that means the corresponding variable is free. We get a parameter, and that means we can come up with a non-zero solution. So let's reduce. We've got a leading 1, so what are our first two row operations? Row 2 plus 2, row 1 becomes my new row 2. Row 3 plus row 1 becomes my new row 3. 1, 0, 3, 0, 3, 6, and 0, -2, -4. And you can maybe see what's going to happen here. What do we do next? So the next thing I might do is do 1/3 row 2. Make that my new row 2. 1, 0, 0, 1, 2, 0, -2, -4. I've got my second leading 1, and now I can use it to get rid of the 2 below there. So if I do row 3 plus 2 row 2 and make that my new row 3, what do I get? 1, 0, 3, 0, 1, 2, 0, 0, 0. Okay, so we get down to a reduced row echelon form where there's a row of zeros, right? So now, if we were solving this equation, right, a times x1, x2, x3 equals 0, 0, 0, right? That's essentially the system, right? So then we would go to the augmented matrix, A with a 0, and we reduce down, we get that down to the reduced row echelon form, and it looks like 1, 0, 3, 0, 1, 2, 0, 0, and right, so put that column of zeros back in that we didn't bother to write, and what does it tell me? It tells me that x1 could be -3 x3, x2 could be -2 x3, and x3 is free to be anything. So since x3 is free to be whatever it wants, it doesn't have to be 0. If I put x3 equal to, let's say I put it equal to 1, right? That's going to give me x1 is -3, x2 equals -2. That suggests that -3 v1 -2 v2 plus v3 equals 0, right? So that's not 0. That's not 0. That's 1 times v3. That's not 0. So this tells me that the vectors are dependent, right? Because I found a linear combination of these vectors other than the trivial linear combination that adds up to give me the 0 vector, right? The way I would have known if these ones were not independent, the way I would have known they were independent is if I ended up with a 1 in this spot rather than a 0, then I would know that the only solution is everybody equals 0, and I'd be done. Now, notice that, this system, if I wrote this system in matrix form, right, this system of equations that we get when we solve for independence, we mentioned this in class, right? Questions about independence are closely related to questions about null space because, if I take A, if this is my A, right, then this equation here is simply A times the vector x equals the vector 0, where x is the vector containing these guys as components, right? We see that here, right? So the other way to think about what I'm doing here, the other thing you could think about what I'm doing is I'm trying to solve for the null space of my matrix, right? And so in that language, in this language of null space, I guess what we could say is that these vectors are linearly independent if and only if the only vector in the null space of this matrix A is the zero vector. Since we found examples of non-zero vectors in the null space, we know that they have to be dependent. Okay? So here's one more example. Let's say I want to determine the null space of this matrix here. So remember, the null space is all of the vectors x, so that A times x equals 0, right? So that equation, think about, so A times x equals 0. In this case, x is going to look like x1, x2, x3, x4. Okay, so the system of equations would be 2x1, 0x2 minus 3x3 plus x4 equals 0, minus x1 plus 4x2, 2x3, 3x4 equals 0, and so on. So we know how to solve this. We set up our augmented matrix. We reduce. In fact, we'd have zeros on the right-hand side, so it's enough to reduce A. Okay, so we want to reduce A. So probably the first thing I'm going to do here is I'm going to swap row 1 with row 2. Minus 1, 4, 2, 3, 2, 0, minus 3, 1, 0, 8, 1, 7. Okay, and then I'm going to do, well, again, maybe I won't bother to write this one, so I'm going to switch the signs on row 1. So that's going to become plus 1, minus 4, minus 2, minus 3. Okay, then I'm going to do row 2 minus 2, row 1. To use my leading 1 to get rid of the 2. 1 minus 4 minus 2 minus 3, 0, 8, 1, 7, 0, 8, 1, 7. How about that? Okay, so what's next? Row 3 minus row 2 is going to be my new row 3. 1, minus 4, minus 2, minus 3. Well, let me skip writing down that step. We know that's going to give me my row of zeros. Let me also do 1 over 8 row 2. I'm going to make that my new row 2. 0, 1, 1 over 8, 7 over 8, 0, 0, 0, 0. And then let's go all the way down to reducer echelon form. So I got to do my backwards step. I got to go row 1 plus 4 row 2. Make that my new row 1. 1, 0. 4 times 1 over 8 is a half, so minus 2 plus a half leaves me with minus 3 over 2. Minus 3 plus a, okay, here I'm going to do 4 times 7 over 8, so 7 over 2. Minus 6 over 2 plus 7 over 2 leaves me with 1 half. 0, 1, 1 over 8, 7 over 8. Okay, there's my reducer echelon form. So what does this tell me? Right, I'm trying to figure out which vectors satisfy A times x equals 0, right? And so remember that this represents x1, x2, x3, x4. Leading ones in the x1, x2 columns, right? So remember, I kind of, setting everything there. There's the column of zeros I don't bother to write. So the first row tells me that x1 is equal to 3 over 2x3 minus 1 half x2. The second row says x2 is minus 1 over 8 x3 minus 7 over 8 x4. Sorry, this is a 4 here. Okay, and that means that if I plug those in, x looks like 3 over 2x3 minus 1/2 x4, and then minus 1 over 8 x3 minus 7 over 8 x4, x3, x4. So if I split that up, x is going to look like x3 times 3 over 2 minus 1 over 8, 1, 0, plus x4 times minus 1/2 minus 7 over 8, 0, and 1. Right? So these two vectors, this guy here, those are going to be the basis vectors for the null space, right? So any element of the null space is going to be written as a linear combination of those two vectors by choosing values for x3 and x4. Okay, that's it for this one.